Right, we're going to kick it off. Good morning, everyone. My name is Tevin. I'm the Kickstart executive here at Pathway CCM. Very shortly, we're going to hear from Joe, Will, and John. But before I do hand over, I do want to turn your attention to the chat box down below on your screens. If you have any burning questions that you'd like to get to, do feel free to ask, and I will raise the question. Otherwise, at the end of the presentation, we'll have a few minutes to go over any questions that you'd like to know the answers to. If you're watching this session recorded, feel free to email us at student@pathwayctm, and we'll be sure to answer all your questions. But without further ado, over to you guys.
Thanks, Tevin. Good morning, everybody. Delighted to be with you this morning. This is a first for me and my team, so we hope you can enjoy what we've prepared for you. As Tevin said, let us know if you've got any questions, which we'll try and answer as we go or at the end of the session. Today, we've been asked to present to you briefly on how maths can be used in the employment that we do, the jobs that we do. So hopefully we're going to hit that well with this presentation. So some brief introductions. The lesson subject today is maths, and although it's maths based, this slide explains a little bit of what we're going to try and talk to you about today, and how we use maths in our daily jobs, and how it could be a subject which, if you're interested, can be transferred into a career path for you. Yeah, we're going to give you a bit of an introduction as to how and where we use maths, how it plays a part in our daily use as engineers. We'll give you an introduction to us and our company, ESD, and explain to you how maths plays a huge part in everything that we do day to day, and also give you some guidance how that interest can help you with some of your career decisions. Just by way of introduction, this is me and my team. Will Gert is with me today. He's a graduate mechanical building services engineer. Joe Lingard is an electrical building services engineer working with me, and I'm a director of environmental services design, or ESD, but with a mechanical engineering background. ESD are a firm of building services consulting engineers. We employ mechanical and electrical designers at different grades of experience, from apprentice to chartered engineers. We employ CAD draftsmen, building physicians, and 3D designers, as well as all the engineers and support staff that we employ as well. So what the building services engineers do, it's not a very well-known career, building services. We find that we always have to educate people a little bit as to exactly what we do as engineers, but we think it's best understood that building services are the systems that make a building come alive. Most of you will understand a little bit about what architects do, in that they make a building fit within its local environment, or stand out if it's an iconic building sometimes. For most projects, a structural engineer will be involved to help the building stay up, design its foundations and its steelwork or concrete. But building services engineers work in a team with those other professionals, and we design all the systems that make a building work, essentially. Yeah. So you can see from this slide, the heating, ventilation, air conditioning, the lighting, the electrical supply, IT, Wi-Fi, CCTV and security systems. These are all the systems that work often behind the scenes, hidden away in a building, but make the building useful, comfortable and safe to occupy. The role of building services engineers has become increasingly important over the last 20 to 30 years because of the increased knowledge and awareness on global warming, control of carbon emissions and reduction to help mitigate the effects of the world overheating problem. can be greatly influenced by building services. As this slide sort of emphasises, buildings contribute 50% of all carbon emissions that cause climate change. Would that be whether that's related to the use of electricity, and how we use fossil fuels to warm buildings and heat them. It's a combination of all those things. We, as building services, are acting now to try and reduce this. There's continuous changes to government legislation that kind of are increasing the pressure to try and control carbon emissions in buildings and other areas like cars and moving to electric vehicles and the like. But buildings, there is a target to have what we call net zero carbon within the next 10 to 15 years. And that will be to a point where all new homes and new buildings do not generate any more carbon emissions. You can imagine that's a huge step from the position that we're in at the moment. And it only applies to new buildings. The existing building stock will hopefully be dealt with at a later stage and be incredibly difficult to deal with. But all new buildings will be net zero within a short period of time. This makes the decisions that we become involved in much more important. As building service engineers, we start to influence the architecture a lot more because the architecture in terms of the building design, the orientation, the location can become a big factor in how we keep it a building much more carbon cleaner, if you will. Ultimately, aiming to reduce carbon to net zero, we still need to make buildings comfortable and safe places to live, work and play. So we use ever efficient equipment and system design techniques. So some of these involve low and zero carbon and renewable energy that you may have heard discussed on the news and in magazines and newspapers. Yeah, so LED lighting uses less energy than conventional lighting. Yeah, photovoltaics generate electricity on the rooftops of buildings. Heat pumps are a way of generating heat in a much more energy efficient way than gas-fired boilers. Heat recovery on ventilation systems helps us to retain some of the heat that naturally gets extracted from bathrooms and kitchens. We can use solar power to generate hot water now on buildings, and we can use passive ventilation to cool buildings at night time rather than using expensive and carbon costly air conditioning. All these are becoming much more commonplace, and over the course of your adult life, they'll be easily recognised, and some of the areas of engineering that we're involved in will be much more commonplace in conversations going forward. In terms of South Kilburn, this is we're involved today on this presentation because Environmental Services Design are part of a design team looking at the regeneration of South Kilburn. We've been employed by Brent Council as part of a team with the architects, structural engineers, landscape designers and other professionals to help design the redevelopment, which is taking place over a number of phases. As ESD, we've been working across 3 of these phases over the last 4 years. And those phases alone will deliver 600 new homes, or over 600 new homes to South Kilburn. The building service engineers at this stage, early stage of design, we're involved in undertaking the carbon emission calculations that we project for the new homes, aiming at this zero carbon target that the government has set. We'll be looking to plan out the energy supply to the buildings and how this is done in both a carbon efficient way, but also aligned with a much wider district heating system that was being installed across the whole of South Kilburn to provide heat into all the new dwellings. We look at things like overheating of the dwellings and how we can control this so the new houses and new flats become comfortable places to live as global warming becomes a greater problem, and temperatures generally around London and the southeast of England become warmer. And we help in the planning and designing of the systems for each of the new homes. Mentioned before, things like CCTV, access control, Wi-Fi, the heating, the lighting, and the ventilation, all become important factors even at the early stages of the design now. So what I'm going to do is I'm going to pass over to Joe now, who with Will, going to hopefully explain a little bit about where we use maths in some of that work that we do, and I'll pass you across to Joe first.
Thanks, John. Thanks for that introduction into just a little bit about what we do as engineers. So yeah, maths and science really are an integral part of engineering, and it underpins everything we do and how we arrive at the results and, you know, the final finished buildings that we're involved with. The type of maths and the complexity of it will depend on the type of engineering and the type of project. So you know, structural engineers will be using different formula to electrical or mechanical engineers. The accuracy in the calculation is really important, and it can influence the size of systems, the equipment, the costs, and also how effective, you know, that system is. And we don't want to be wasting energy, as John alluded to. There is a big push on that at the minute. We use different types of maths. We use algebra, geometry, calculus, computation. It's all made a lot easier and wrapped up in easy to use software tools, but fundamental knowledge is essential going forward. We use the maths to analyse engineering systems. We use it to calculate lighting levels, so we know how bright or dark a room is. Calculate cable sizes to supply electricity to different areas of the building. We use it to calculate if buildings overheat and the amount of air conditioning that's needed and how much energy that will use. And we also use it to calculate pressure losses in pipes and ducts. So it's used in a wide variety of things, and it's, like I say, a fundamental part of what we do. I'm going to pass you over to Will now just to do a quick introduction. There you go, Will.
Yeah, so Joe's an electrical engineer, whereas I'm a mechanical engineer, which deals with more stuff like the heating and the cooling and the water and drainage of systems in buildings. So for when we do this, we use lots of formula, but the most common formula we use to do the heating and cooling is a specific heat capacity formula, which relates how a change in temperature affects the energy of a material. The Q equals mc delta T. That's the fundamental equation that we use. I use it every day. That's the most commonly used, but it's the most important one because it tells you what heat you need in a building. But we also use more complicated equations, like on the right here, we've got Bernoulli's equation, which is an equation that relates pressure, velocity, pipe size, and other things for a fluid in a pipe. And we can use that first principle. We can use that first principle to take it to something like an orifice plate, which is in the bottom left. So an orifice plate is just a device that we use to measure how much flow is going down a pipe, and we can use the difference in pressure at two different points of a pipe to work out what the flow going down the pipe is. I mean, we don't want to have to work this out from first principles every time. So we've actually got software or tables that we can use the pipe size and the difference in pressure to then work out the flow in the pipe, so we don't have to do this complicated equation each time. So go forward. And then there's also more complicated things. I said we needed to use Q equals mc delta T to work out how much heating we need in a building or how much flow we need down the pipes. But for that, we also need to know how much energy is lost from a room, so how much heating you need to put in. And we use something, we do that by calculating heat losses. And there's loads of complicated formula there, which you can use to work out how much heat's lost through a window, how much heat's lost from room to room. You might even gain heat through your windows from the sun. I mean, these are all, you can do all these by hand, but we have a fancy software where you build a 3D model, you input the rooms, the walls and window types, and then it will work out for you how much energy you need to heat and cool a room. And that's something that is fundamental to what we do.
Yeah, so this is an electrical based equation that's used daily by electrical engineers. It's Ohm's law, the power triangle. This is basic principles, and like I say, it's used daily, but it's a very simple calculation. We've got an example of it later on, how we use it. I mean, this was developed in like the 1827, and it's still true to this day. The power triangle, it gives us the electrical energy that's transferred in each second, so we can work out the size of cables and the circuit protective devices that are needed, and how much energy is going to be used in the building. These are the foundation and first principles. We need the understanding of it, but again, it's now been speeded up. We've got design tools, software, tables, as Will mentioned, that we can quickly refer to get the answer to the questions that we need. If you want to move to the next slide, John, we've got another example here of our mathematical equations used. So this would be used in lighting design. This is the inverse square law. Basically, the intensity of the light will decrease with distance from the source. This allows us to calculate the amount of light on a surface at a specified distance. Again, we're not having to use this exact equation daily. It's built into software packages that we can then manipulate easily. We build a 3D model, we can place light fittings in areas and use that then to calculate the levels that we're going to get in certain spaces and areas and walls. I'll just pass you over to the next slide.
So for some jobs we do, for some projects, we have to do more complicated things. So what you're seeing here is an image from a job in the University of Salford, where they're wanting to build a chamber that can they can change the temperature from -20 to 40 degrees, so that then they can build a house in it and see how energy efficient it is at different temperatures and different environments. So that's a very, very complicated design. And to do that, we use something called a CFD, or a computational fluid dynamics, which then allow us to see, because we need for lab conditions in here to be able to do the experiments to see how the houses do, we need a very stable environment. So what you can see in the two photos is that we've introduced a 3 kilowatt heater. So at 3 kilowatts, that's about what you get for a kettle. You can just see how the model shows how just a bit of heat in the corner of the room there will change how air and the temperature is distributed throughout the building. Yeah. Do you want to move on, John?
Yeah, so again, this is another example of the software tools that we can use. It's all based on that first principle, math calculation. This is a lighting calculation done for Norfolk County Council chambers. They've got a big refurb project going on down there at the minute. There's a large marble wall with like a map on it. We needed to calculate the lighting levels in that area so that they were safe, and adequate to carry out tasks. But also we were concerned that the marble wall might give off lots of glare. So there's calculations that we can do that. You feed it into the model, and you can see there in the bottom corner there's a 3D image of what we're looking at. And yes, we can sort of analyze the data that the calculation produces. We can set different calculation planes up to pinpoint specific areas in that room. to make sure that we're happy that everything's, you know, safe and a good environment for people using that building. Okay, that's me.
So I think we're just going to go through a few quick examples of some of the equations that we use in every day. So as I said, this is a specific heat capacity, and you're just gonna, I mean, I don't know if you got some paper and a calculator you want to quickly try and work this out while I explain why we would use this. So this would be if we knew we had a pipe with like 2.8 kilograms of water flowing down it every second, we could then use the specific heat capacity. And if we knew the water was going at 80 and coming back at 70 degrees, we could then use that to work out how much heat was going out to, say, the radiators or whatever other heating device we had in the rooms. So I'll give you a few seconds to try and work it out, and then I'll let you know the answer.
So we're trying to calculate Q, the heat energy here, Will, yeah?
So we're working out Q. We've got M is the mass, which is 2.8. C, specific heat's 4.18. And the delta T, as I said, was 10 degrees.
Yeah.
So, well, to move the presentation along, the Q in this is 117 degrees. 117 kilowatts, sorry. And then we can use that helps us size. We know the flow, we can then help size as the heating systems and the pipes we need around the building.
Well, we've got an example a bit later on of where we actually use that figure of Q, the heat energy, where it becomes important to us for helping to size, as Will said, heat emitters, but then also the pipe work and the system that connects all the heat emitters together. And it seems a very simple, basic calculation. But the importance of this is it demonstrates that, you know, simple maths done well and correctly can play a big part in a professional career.
Thanks. Yeah, so we've got another example calculation here, an electrical example, and this is used to find the currents in, this example is an electric shower, but this could be any piece of equipment in a building. It could be a motor in a factory, a pump in a heating system, flood lighting, car chargers, anything. And we use this calculation to work out the current so we can size cables that are serving the equipment and to select protective devices that are used for safety to prevent electric shock or the faults in the system. Really easy, you know, maths this. It's very basic, but it comes in handy. So I'll probably use this multiple times a day in my career. And yeah, it's fairly straightforward. So we've got the power rating for the shower in watts. That'd be this example, 7.2 kilowatts, 7,200 watts. And the voltage, system voltage in the UK is 230 volts for a domestic property. And we can see there by using the triangle, we want to calculate I, which is the current. And that would be then power divided by voltage. And it's fairly straightforward. The answer there I can tell you is 31.3 amps. That would help us, yeah, size the cable. There's other things that we have to take into account. You know, there's other regulatory items that we need to consider, but this would be primarily used to size cables and select protective devices for the building. And yeah, it's dead simple, but it just goes to show, you know, it comes in handy.
Yeah, as John was saying earlier, this is the slide he was talking about. So we might be able to work out the pipe size, but we've got to be able to show it on something so that people can use it. So we put it on something we call a schematic, which basically just shows the whole heating system on one drawing. So on this, you can see we've got different rooms with radiators in, say that corridor there or that, yeah. And then we can see how these have the pipes that go back up to high level and then across into a big pipe that runs up and down the building. These pipes, then you see on the very left-hand side of the drawing, there's a pump, which is what pumps the water around the building so that you can get the water at the radiators. So we need to be able to size this pump. So for that, we need to use, you see all these, there's loads of numbers across the drawings. These are what we call crosshairs. And if you see at the bottom right, we show what the crosshairs mean. So the flow rate, that's the M from the Q equals MC delta T. And that's just the amount of water that's flowing down the pipe. We've got the pipe size. But then when you've got an amount of water going through a amount of pipe, it's going to flow at a certain velocity. And we need to make sure we have the right velocity, because otherwise water going too fast down a pipe is too noisy. And then in the bottom right, we've got the pressure drop. So as water goes down a pipe, if the smaller the pipe, the harder it is to push the water down the pipe. So this pressure drop in the bottom right is crucial for when we are sizing the pumps, because we don't want to have this too high a pressure drop, or we have to have a bigger pump, which is more expensive, and nobody wants that. No one wants to spend the money on that.
It helps. These type of calculations also help us in some of the aim to try and reduce energy consumption. Energy consumption usually means higher rates of carbon emissions, and if we get our calculations right here, size the pipe work correctly so that there is not excessive pressure lost down the system, as Will explained, we can size those pumps efficiently, and then make the system overall much more carbon efficient, which helps the building to be more carbon efficient.
So this is just an example of what we were going on about, how this room it can lose heat through windows or doors, or it can lose the roof or stuff, but it can also gain heat from the sun. So you need to be able to work out what size heater you need to keep that room at 25 degrees or whatever temperature it needs. But then when you get in the room, it's more complicated than just putting one heater in the middle of a room. You can see that the radiator actually works through convection. So it blows the air around the room, the hot air rises, rolls across and drops down and comes. You can also see on that, we need to take into account stuff like computers and people. They also give off a lot of heat, which when you come into air conditioning a room, it's vital that you take those into account.
To give you some more images really out of some of the software tools that we use, one of the types of engineers that we employ, we term them building physicians, and they spend all their time analysing how a building's performance is going to work, using some of the calculation software tools that we were spoken about with Joe and Will. But more specifically, they're looking at the energy consumption, and they use really complicated computational models to build the building itself within the software, and then we can use this to move it around the site and see how it interacts with, in this example, the pathway of the sun, the orientation of the sun. Solar effects on a building can be huge. It can help with solar heating. It can be a hindrance because it adds too much heat that we then have to take out to air conditioning. The line of the sun on a building can help with shading, and it can help with things like renewables, particularly the selection of solar photovoltaics. So we use all these interactions between the engineering that John will do, and also in the building physicians, help to get the most efficient position we can on the building. And then ultimately, we translate all these calculations into a design. It might be a difficult slide to read here, but this is a project that we are currently working on. To the bottom of the screen, this is a new Riverside stand at Fulham Football Club, and you can see the tiers of seating here, the roof over the stand. I think this project's actually got a swimming pool on the roof, and there's buildings down the side as well for officials and press and things like that. But on the left-hand side, you can see a representation out of our 3D model. We draft all our systems designs in 3D now, and these are designed to help to coordinate all the routing of the pipe work and the duct work, the electrical containment, the position of light fittings and heaters, ventilation equipment, all within the building. So this drawing at the top is what's hidden away behind the stand that you see on the right-hand side. So I just thought it'd be good to also let Joe and Will explain a little bit about how they got into engineering with their background. So I'll flip back to you, Joe.
Yeah, basically left school, didn't really know exactly what I wanted to do. Finished with GCSEs in maths, English and science. Basically enrolled as an electrical apprentice at college, and I went working for a local plumbing and heating company. We were just wiring up boilers and heating systems, domestic buildings. Went to college sort of 1 day a week. Worked as that for a few years, numerous jobs really, floated about. Worked as a self-employed contractor for around 10 years, and then I sort of progressed to larger projects there, including healthcare and educational buildings. And really there I got more of an interest in sort of the planning and design of all the building services, and instead of just installing them, I was more interested in how they all go together in the process of designing the building. That led me to enroll on a degree course after completing the foundation degree at a local college and university. This sort of challenged me in new ways, develop new skills. But the time that I had as an apprentice in an industry and installing the systems that I'm now designing has been valuable, and the experience that I've gained there, it's really helped me during my further studies, and as my role now as a design engineer. That's basically me in a nutshell.
So I did GCSEs like Joe, but then I went on to do my A levels. I did A levels in maths, further maths, physics, and biology, and then I decided to go off to the University of Liverpool, where I went and got a master's degree. Whilst I was at university, I came and worked for ESD part-time over the summer, so that I could just to earn some money to survive at university. And so while I was here at ESD, I started off as a CAD man, just drafting up the drawings as we've seen earlier. But then as I came back each summer, I moved more and more into the engineering side of it, doing more of the simple calculations and doing more complicated. And then after I finished my job, John and the other directors were kind enough to offer me a full-time job. And as I was enjoying it, it was interesting to me. So I decided to carry on being here at ESD full-time.
Thanks, guys. Just to finish off, really, I mean, hopefully you've got a bit of an insight into what building services is. It's a fairly little known profession, particularly within school groups, from my experience, but we've got a growing reputation, and we can start to make a real influence on issues like global warming, carbon reduction. I've been a building service engineer all my life, 40 years, and there's an amazing amount of job satisfaction that you can achieve from this career. Linking yourself to the buildings that you've been involved in, but also there's a whole range of available career angles within building services. I've just listed some there. Things like services designer, consultant engineer, energy consultant, estimators and researchers, maintenance engineers, contractors, and project managers are all in the same field of building services engineers. And as Joe and Will have shown, there's different entries into the industry, whether that be GCSE to college, to university, to employment, or through an apprenticeship, or through a trade, and then ultimately ending up as a designer. There's multiple angles in, all of which can be investigated really. And we have an institute that is been hugely supportive recently on bringing younger engineers into the industry. The CIBSE is our institute, and they've been, like I say, incredibly active. They now run Apprentice of the Year awards, and you know, that's been great to promote services into the wider angle of things like schools, careers evenings and the like. Yeah. So there we go. That's us. Hope we found that a little bit interesting and informative. I'm not sure if there's any questions that have come out of that, Tevin, that you want to be able to throw at us.
Yeah, absolutely. And thank you, gents, for that absolutely amazing presentation. And I know there's a lot of value in there. We have a question from Afiola. As a mechanical engineer, do you use CAD software as the layout for your schematics?
Yeah, we use CAD every day basically. So that schematic was drawn using CAD software called AutoCAD that we use. But also we use the computer also to do the 3D models in something called Revit. We use to be able to model everything. So we basically use CAD in every day. Both me and Joe will both use it.
Absolutely. Are there any more questions? I'm actually quite curious to know, for an engineering student, is there any tips or advice you'd give them going into the industry?
Yeah, I guess you need to do something that you enjoy and find interesting, really. So, from a young lad, you know, I was always sort of interested in building stuff. You know, my dad was doing DIY, got involved, and that's how I got into being an electrician. And from there, it just sparked the interest, really. Yeah, so I'd say definitely, you know, you need an interest in it, but it's a rewarding career. There's lots of different avenues you can go down, like John mentioned. So, I mean, as well, you can do something different every day, really. So it is a good thing to get.
I think to add to that as well, Tevin, if students are interested in a career in engineering, is to do a bit of research and see what options are available. I mean, we all know, we've all heard of mechanical engineers and electrical engineers, but the field is much wider than that. You know, hopefully we demonstrated that building services engineers, it does involve electrical and mechanical engineering, but partly in a softer way. You know, we're not designing aircraft engines here or big nuclear power stations. We're involved in designing systems that you take for granted when you go into a building. You know, those you flick a light switch, the light comes on. There's a piece of work gone into ensuring that that light does what it's supposed to do, and that the cable and the protective device on the end of it. And I don't know. I think it's a very underrated industry, the building services, and I think there's if somebody's interested in engineering, it's certainly worth a look, and to widen your horizons if engineering is for you.
Absolutely, absolutely. Thank you, John. Just really conscious of time. In the chat box, I am going to put a link to an insight they were hosting on 14th of July at 5:30 p.m. It's a chance to hear more about Pollard, Thomas Edwards, and also for a chance to get involved in some work experience. So it's definitely a session worth attending. And again, it is in the chat box right now. And for the people that are watching and recording, feel free to email in at student@pathwayctm. I'll be more than happy to answer any questions you wanted to ask during this presentation, and more so learn a bit more about the event we'll be hosting on the 14th of July. But again, on behalf of Pathway CTM, thank you all for joining, and thank you, Joe, Will, and John for sharing the value that you have. Thank you.
Oh, great. It's been good. Thanks.
Yeah, thank you, Tevin. Yeah.
Cheers, gents. Thank you.